Okay. I'm gonna get started. People should show up. So. The first set of assignments. So that's the worksheets for chapters 2, 5, 6, and 7. And the homework are all on Brightspace in the homework and worksheet sections. And they're all due on the 11th when we have our first test. So our first test will be not this week, but next week on Thursday. And that will be on chapters 1 through 7, basically. Remember to sign in on the sign-in sheet up front for attendance. Yeah, I guess we'll just get started. So, why are you not working? Yeah. So, last time we discussed light, and light is how we observe the universe primarily. Up until very recently, 2015? No. Yes, 2015. It was the only way we effectively were able to observe the universe. Beyond us. That's when we first managed to detect gravity waves. But to observe things very far away with light, we need to use tools that detect that light and concentrate that light so we can bring it to a level where we can actually observe it. And those are telescopes. So this chapter is going to be about various types of telescopes. We'll start with the oldest type, optical telescopes. The kind of telescopes that you could, in theory, look through with your eye. The modern telescopes are all set up to have digital detectors attached to them, basically cameras, because that's just more convenient in many ways. So a telescope is a device used to observe astronomical objects. The primary purpose of a telescope is it takes light from a large area and concentrates it into a small area, so it generates enough light to be observed easily, or more easily. Yes.
So a telescope isn't like a mirror on top of another mirror.
That's how you do it, but you can make a telescope with lenses, you can make a telescope with mirrors. But the main idea of what a telescope is as a tool in astronomy, at least, is the goal of a telescope is we have a big area that light is coming in, and we focus all that light down into a small area so it can be detected easily, because we're trying to look at very faint things. Now, that's its use in astronomy. It has other uses, like it makes images look closer. So it provides magnification. That's more what you would use it for if you're looking for things on land. But it makes distant things look closer. That's the use we have for it when we use it, like to observe things on Earth. But as for astronomy, there's not much different, the magnification is one of the least important aspects of it. But, and when we start to spread beyond optical telescopes, they don't always use mirrors. You know, you might use slightly different methods. But the general idea is it's a tool that gathers light or other types of electromagnetic radiation and brings them to a focus, allowing you to observe fainter objects. Because many of the things we want to see are very faint. So the main goal with the telescope is to see something faint or small. So the telescope was invented in 1608 by Dutch lens grinders. So the first telescopes used lenses, not mirrors. It was invented in 1608. Dutch lens grinders who'd been making lenses for things like spectacles, glasses, and such. And eventually one of them realized that if you put two lenses with each other, you can see things far away. Galileo heard about this and made his own. From the description, he ground his own lenses, made his own telescope in about 1610. And Galileo was the first person to observe the sky and record and publish his results. Given that the telescope had existed for a couple of years before he made his, he probably wasn't the first person to observe the sky, because, you know, somebody probably looked up. But he was the first person to, observe the sky and actually record his results and publish. So there's two main types of optical telescopes. There are refracting telescopes. They use lenses. The light is bent via the method of refraction and brought to a focus. This is the first type that was invented. And reflecting telescopes. They use mirrors to focus the light. There's a curved mirror that bounces the light up to a focus, and usually another mirror that knocks it out to where your eye would be, or back. There's another exit. There's a few different ways you can set that up. So refracting telescopes are the original type of telescope, but they have issues with scale. They don't work so good when you get really big. So all modern serious research telescopes are reflecting telescopes. They use mirrors. There's a number of advantages to using mirrors as well. But for day to day, if you want to observe stuff at night, my suggestion, get a pair of binoculars. Binoculars are basically just two telescopes, one for each eye. And sometimes they have a little bit of funny optics in them to make them shorter. Basically, they bend the light path so that they're effectively longer than their actual length. But if you use binoculars, those are effectively refracting telescopes. They use lenses, that's their primary thing. If you've used a zoom lens on your camera, or you've seen a telephoto lens, those are refracting telescopes. They use lenses. But for astronomy, for like serious research, most stuff is done with mirrors, just because these days we want to get as big a telescope as possible. And at scale, mirrors are just much better than lenses. So you can have a reflecting mirror that brings light to a focus. It's a curved mirror, so parallel light bounces off the curved mirror and comes to a focus. So all the light from this large area is focused into this small area, so it's easier to take images. Or you can have a refracting lens that bends light, like prism. By the fact that light bends when it enters a different material and brings the light to a focus. The issue with using lenses is that there's you can have certain lenses don't scale as well. Really big lens is harder to work with because you have to hold it only by the edge. Unlike a mirror, which can support the back. Additionally, there's something called chromatic aberration. Where in lenses you can have different colors bent to different amounts because they act like prisms. That doesn't happen with mirrors. So here again, these are reflecting and refracting telescopes. This is sort of the original Newtonian design. The reflecting telescope was invented by Isaac Newton. And here is a refractive telescope. So modern telescopes are all reflectors. One of the big issues is something called chromatic aberration. The light traveling through a lens gets refracted differently depending on its wavelength. And basically this causes rainbows around any point source. This is a real problem in camera lenses that they spend a lot of effort fixing. Some light traveling through a lens gets absorbed because it has to go through a material and that absorbs some of the light. And then you get less light, and your goal is to get as much light as possible, so that's the problem. And a large lens can be very heavy, and it has to be supported only at the edges, which leads to possible distortions, or it's just much more difficult to work with. And a lens needs two good surfaces. Both sides of the lens matter. So both sides of the lens need to be optically acceptable, but a mirror only needs one. Now, it's not that we don't make big lenses and still use them in telescopes, but they're not the primary thing. They tend to be at the end, after the mirror. So often you have like a mirror, another mirror, and then maybe a lens at the end at the eyepiece kind of position. So this is sort of an idea of how an image will form. Basically, if light is coming straight in from the center, it comes to the center. If it's from the bottom, light from the bottom of the source, blend up a little higher. Light from the top of the source, blend up a little lower. And you'll get an inverted image form. That'll be much smaller and brighter. So, when you're dealing with reflecting telescopes, we can divide them based on how they get the light out. It's what they're called their focus. So the simplest is a prime focus. It has one mirror at the bottom, the light focuses up at some point, and you put your detector there. Prime focus telescopes aren't that common. Because usually we don't, well, they are that common for optical telescopes using visible light. Radio telescopes tend to be prime focus. If you've ever seen a satellite dish, it's a dish with a detector at the focus. That's a prime focus. But optical telescopes tend not to use this because you have to get your detector out in space over here. It's inconvenient. So much more common are things like a Cassegrain focus, where there's a secondary mirror here, and it bounces the light back through a hole in the primary mirror. And so the light comes out back. And then you can put all your detectors and stuff behind your telescope in a convenient location. There's also a Newtonian focus, which is the design of the first one of these. This is commonly how, like, if you buy a telescope for personal use, a smaller telescope, they tend to be Newtonian focuses, where the light is reflected onto the side of the telescope, which is a convenient place to put your eye. But this is not, Cassegrain focus is much more common for larger ones. There's also a fourth design called the Dansby setup. So those are the three: the prime focus, Newtonian focus, and Cassegrain. And there's also a Nasmyth or Coudet focus, which is like the Cassegrain focus, except another mirror knocks it off the side. A decent number of large telescopes have both these two, the Cassegrain and the Nasmyth. So for one set of instruments, the light goes through out the back, and for another set of instruments, it goes out through the side. And sometimes this is set up as a beam splitter. So half the light goes out the back, half the light goes out the side. Or you can switch, depending on what you want to measure. So sometimes it's set up with a beam splitter, sometimes it's set up with a mirror that you can open or close to choose whether it goes out the side or out the back. And you have different sets of inframints over to the side and over and behind. So the powers of a telescope, how you rate the strength of your telescope. They are light gathering power. So this is how much light your telescope can get. This depends on the square of the size of the primary lens or mirror. Larger is better. Basically, the more area your main lens or main mirror covers, the more light it can grab and focus. Then there is resolving power. This is how small of an object in the sky or you can resolve. You can see the difference between. This depends directly on the size of the primary lens or mirror. Again, a larger mirror or lens will have a smaller resolution, a better resolving power. So basically, the bigger your telescope is, the finer the detail you can see. And this just depends directly on the size of the primary lens or mirror. Like it's based on the size, it's not based on the area. It's based on like how far apart the most distant edges are. And then lastly, there's magnifying power, which depends on the focal length of the primary mirror and lens and the focal length of the eyepiece. And this is the least important factor for actual astronomy, because most of what we're looking at are points, even when you magnify them. So more detail isn't that useful. So this is the least important thing. So resolution is much more important than magnifying power. And it's relatively easy to add more magnification after the fact, or so here's an example. This is the Ch6 telescope in Hawaii. So it can do, well, it has both a Cassegrain focus and a Nasmyth focus. So the incoming light comes in, bounces off the large mirror, which is so big they actually made it as 36 separate segments. That's fairly common these days. Mirrors are getting so large they don't want to make them as one piece because they're just too big and awkward. And you have to move them to the telescope. Telescopes are usually in quite remote, inaccessible areas. And the places we make mirrors are not near them. And so there's the primary mirror, which is in 36 segments, comes up, hits the secondary mirror, and bounces down to this thing here, which can split the light or can reflect the light either out the side to the Nasmyth focus in the Coudet room, which is a particular technique. And the advantage of this side focus is that I believe this is on the actual axis the telescope rotates on. So none of the lengths change and nothing moves particularly. Or it moves less. It's easier to the stuff about you use a Coudet room, you need to be very controlled in how far the light travels because it involves interference. And then there's the Cassegrain focus down in the back where the primary detectors are. So the more light gathering power, the fainter things you can see. So here, the brightness is proportional to the square of the radius of the mirror. Here, this telescope down here. This is the same galaxy. You can see this one's quite a bit brighter. The lower picture was taken with a telescope that's twice the size of the upper picture. So by doubling the mirror, we quadruple the light gathering power. And as you can see, it's much brighter. You can see much fainter objects. So here, for example, are some images to give you an idea of the size of telescopes. These are the group of telescopes on top of Mauna Kea in Hawaii. So there's the two Keck telescopes, the Subaru telescope, the Canada, France, Hawaii telescope, the Gemini North telescope, the smaller United Kingdom infrared telescope, and the NASA infrared telescope. This is the Very Large Telescope in Atacama. All four of these are part of the Very Large Telescope. And nearby is where they are building the new biggest telescope in the world, the Extremely Large Telescope, which is currently under construction. Yeah, they ran out of interesting names. But now, another advantage of a larger telescope is you get better resolution, more resolving power. Makes things less fussy. So here, this is taken with a smaller telescope, and this is with a larger telescope. Because you can compensate for getting less light by observing for longer. But resolution is something that you can't compensate for easily. So here we have a fuzzier image, and here we can see finer details because this is taken with a larger telescope. And resolution is proportional to wavelength and inversely proportional to telescope size. So you can get finer resolution the bigger your telescope is, or the shorter the wavelength. Because the thing that determines resolution is diffraction. And so it has to do with the ratio of the telescope size to the wavelength. Which means if you're looking at a very long wavelength, like radio waves, your resolution is going to be garbage with a small telescope. So you need a really big one, which is why radio telescopes are also huge. So here, for example, is an effect of increasing resolution. We get bigger and bigger telescopes, getting more and more details. And these are the resolutions in degrees, 10 degrees, 1 degree, 5 seconds in 1 second. Those are the resolutions observed. That's arc degrees and arc seconds of the sky that can be resolved. Now, some limitations of telescopes. One of the issues that refraction has is something called chromatic aberration, where lenses will act like prisms. They'll bend the light to focus it, but they'll bend each wavelength a little differently. And this creates basically rainbows around it, like a point source of light, like a star. And this is problematic because it blurs your image, spreads your colors out, which isn't great. But usually images are taken for astronomy, they're taken in black and white. So the problem here is that it blurs your image. But it's a real problem in photography and anything else that uses images. There's limitations to the size. You need to be able to move and support and move the telescope. So probably the extremely large telescope is reaching the limit of the size of a telescope we can reasonably build on Earth. It's getting so big, you wouldn't be able to like point the telescope in a sensible manner. And then lastly, there's what's called seeing. The atmosphere is made of stuff, and that stuff can bend light. And it's not sitting still. The atmosphere isn't sitting still, it's turbulent. And so because there are turbulent layers in the atmosphere, they basically perturb the waves that are coming in, and they blur objects. And there's ways to correct this. There's something called adaptive optics, where they distort the mirror to correct for the distortions from the atmosphere. So there'll be tons of little motors on the mirror that can bend it and reshape it or redirect it a little bit, things like that. But that is just a fundamental limitation of being in an atmosphere. You're going for an atmosphere, there's stuff there, it's going to disturb and bend the light. And it puts sort of a limit on how far the fairly you can see. So I think the air is constantly moving around, it's gonna, deflect the rays slightly, and that effectively blurs things. So how do we deal with this? Well, if we want to see things in great detail, we want as little an atmosphere with as we want to be looking through as little atmosphere as possible, and we want that atmosphere to be as uncomplicated as possible, as still as possible if we can, but mainly we want it to have less stuff in it. So we put telescopes on top of mountains. So they're above lots of weather and things like that, especially in deserts, because wet air distorts light more than dry air. And it causes more turbulence as well. So we put them in wet, dry, high altitude locations. Another solution, we put our telescopes in space, no atmosphere to worry about. Problem with putting a telescope in space is you have to get your telescope to space and build your telescope such that it can go to space. So there's limitations on how big you can make it, which is why the James Webb Space Telescope, our current biggest space telescope, had to be sent up to space all folded up. And then I had to unfold to reach its final shape. Let's see what people are saying in the chat. Someone mentioned why not build it on the moon? There is a proposal to build a large telescope on the moon. Like that's actually something that's been proposed and sort of brainstormed. The main problem is, you have to get up to the moon and build stuff on the moon, something we haven't done yet. But there's actually a proposal out there to build a telescope on the moon. Particularly on the dark side of the moon. Well, no, it wouldn't be on the dark side of the moon, it'd be on the far side of the moon. So you wouldn't have to deal with Earth. But it would only work like half a month. But yes, and then so the other issue is that on the moon, half the time it's day. You have the sun shining on you, and that period lasts like half a month. So there's some disadvantages there. And lastly, we use active optics. We control mirrors by bending them slightly to correct for atmospheric distortion. And that can take you from something blurry-ish like this to something much sharper. So with active or adaptive optics, we do thinner or segmented mirrors. And then there are motors behind these mirrors that can either change which direction they're pointing or bend them, or both. And these are computer controlled, and they can deform their shape to account for atmospheric turbulence. And here is actually one of I think this is the Ch6 telescope. The Ch6 telescope has a powerful laser that it shoots into the sky to basically create an artificial reference star that it uses to set up its active optics. So you shoot a laser out to create something where you know what it should look like. And then you image that and adjust the optics until it looks right. And then you can start taking pictures of other stuff out in the sky. But that lets you correct for the current weather conditions. Because they change, because the atmosphere is a complicated, messy, turbulent thing. But yeah, any telescope in space just is going to be much harder to, access and work with and stuff, even if it was like on the moon. The advantage of telescopes on Earth is that you can go there. So here are some modern astronomical telescopes. This is the Hale telescope at Mount Palomar. It was completed in 1984. For a decent period of time, it was the largest telescope in the world. It had a 200-inch mirror, 5.1 meters across. This is the Very Large Telescope. It was completed in 2000. It has 4 8.2 meter mirrors. And it can actually do interferometry, where it can combine images from multiple telescopes, multiple of these telescopes, to create something that acts like a larger telescope with better resolution. And there's a couple of little telescopes that aren't in this picture. They're off to the side. They effectively, for interferometry, make it even bigger. So this Very Large Telescope was actually able to take the first image of an exoplanet by using interferometry. And interferometry with visible light is actually really hard, because you have to perfectly adjust the lengths of the paths the light from each telescope are taking to combine them properly, so you can get a combined image. So they have this really complicated underground tunnel that can adjust how the light travels from each telescope to bring them all together. The most impressive interferometry we do is with radio telescopes. But with radio telescopes, the frequency is low enough, you can actually do it all digitally. So we just record like exactly the signal from each telescope and we combine them digitally. And the most impressive version of that is the Event Horizon Telescope, which used radio telescopes all over the world to effectively create a radio telescope that was as big as the Earth and image a black hole. This is the Large Binocular Telescope. It was completed in 2004. It has 2 8.4 meter mirrors. You'll notice a bunch of these have mirrors that are all the same size. It's because there's 1 or 2 places that makes mirrors. Because this, these take specialized technology like spinning ovens to make these mirrors to have the right shape. Here's the Grand Telescope Canaris, which was completed in 2007. It has a 10.4 meter mirror. This is the European Extremely Large Telescope, which is projected to be completed in 2027. Probably gonna take longer, because it's gonna have a 39.3 meter mirror. This thing is huge. This is a mock-up. The construction is progressing. I don't have a more modern picture, but this base structure, the walls of it have been built.
Is that a car at the bottom of there?
Yes. This thing is huge. So here, just there, that's construction equipment. There's like, this is the foundation. And that's been built up, like a few stories at this point, at least the last time I saw a picture of it, which was a while ago. So, I mean, real progress is being made on this. It's not super fast because construction on top of a mountain in Chile is never gonna be easy. But, progress is happening. So, where do you want to build a telescope? Well, if you're building an optical telescope, you know what you don't want? Clouds, because they get in the way. So you need clear weather most of the time. You want to go somewhere that doesn't have a lot of weather. You want to avoid water vapor because it absorbs light and it helps distort images. And you need dark skies, so you need to not be near cities. And you'd like to have good seeing. You need good seeing, so as little atmosphere as possible is best. So the best solution is on top of a mountaintop in a desert. So a number of American telescopes got the on top of a mountaintop part right. They're on Mauna Kea in Hawaii, but they missed the desert part because Hawaii is definitely not a desert. The big collection of telescopes, there were a whole bunch out near Las Vegas, out in Nevada. But those have gotten kind of too near big cities and they weren't quite high enough. And the big collection of European telescopes are all on a mountain in Chile, which is both on a mountaintop and in the desert. So in general, telescopes are used to gather light from distant objects, bring it to a focus. The three powers of a telescope are light gathering power, resolving power, and magnifying power. And the first two are the most important. And modern telescopes use much thinner and larger mirrors than previous telescopes. So the mirrors are much thinner. They're often made of multiple segments these days. And they're much larger. And that active optics thing as well, that's not just for ground-based telescopes. The James Webb Space Telescope has adaptive optics. It's a little different because it doesn't need to change as often, but it does have a set of motors that can redirect, reposition, like what direction, and change the bending on all of the mirrors. So one of the first things it did was basically focused in all the mirrors, so all the images combined properly. And part of that is because they had to send it up, fold it up in a rocket, which is very shaky and stuff. So you couldn't be sure everything was going to stay in perfect alignment. So if you can't make it certain, make it adjustable. Sort of an engineering rule of thumb. So yeah, every mirror has 5 motors on it. So let's talk about how we detect light. So the earliest astronomical detector was the Mark I human eyeball. Well, probably not actually Mark I, but the human eye. You had to draw what you saw. And the problem with this is that it's very subjective. Because not everybody makes a perfect drawing of exactly what they're seeing. It all has to pass through your brain, and your brain fills in gaps, because your brain is adapted to give you like actual information that keeps you from dying and not like perfectly reproducing random images. So there can be issues there. So this actually led to this whole years of people claiming there were canals on Mars, which was sort of a combination of a mistranslation and an optical illusion. The mistranslation was there was an Italian, I think it was Italian, who wrote canali, meaning channels, and an Englishman read that as canals. And then it turns out if you look at Mars, there's an optical illusion where you can see straight lines that aren't actually there. It's some optical illusion, and that helped reinforce this. There are channels on Mars, we've definitely seen those. But they're not canals, they're not artificial. Then we moved on to photographic plates. Photographic plate is a glass plate with a photographic emulsion on it. This has big advantages over the human eye. It can sit there and absorb light for a long time. And you tell it's not efficient. It only records about 1% of the light that hits it. These are difficult to store, and it's hard to share the data from them, but they do have some advantages. Once you make them and properly make them, they last for a really long time in a manner that's easy to work with. Well, it's easy to retrieve the data. So there's actually been a number of discoveries made like recently by going through old photographic plates where they did like surveys of the sky, many, many years ago. And if you have the collection of these, you could extract new information once these photographic plates get digitized sometimes. But in the modern day, the big advantage of photographic plates is they stick around, but they're awkward because they're glass plates, so they're hard to move around. And in the modern day, we use digital detectors. These are called charged coupled devices. You probably have one in your pocket. Same thing is used in the camera in your cell phone. It's used in digital photography, in cell phones, and lots of other things. And these are chips that are such when light hits them, it knocks an electron free, and they're made in little pixels, and in each pixel, the electrons are collected and stored, and then they can all be read off at once. So the electrons pile up over time, and then when you want to read it, all the electrons are read out, and that tells you how bright each pixel is. These are much more sensitive than previous detectors. They're much more efficient. They collect like 60 to 70% of the light instead of 1%. And they have a bunch more advantages. They can be quickly read out and reset. So for a photographic plate, you have this photographic plate, you have to handle it correctly, then you have to develop it and chemically, which takes time. For a CCD, you say, tell me what you saw, and it dumps out the information digitally and feeds it quickly into a computer where it can be immediately analyzed. And so the light strikes the surface, and it produces electrons that get stored. It basically knocks electrons free. So this chip is specially doped so that you get electrons that can be easily released, knocked free, and they pile up in little storage areas, basically. This is very efficient. 60 to 70% of the light gets recorded. And at the end of the exposure, the electrons get counted, giving a representation of the brightness in each location. Each pixel. And large CCDs, like the ones they use for astronomy, are big. And they can have hundreds of megapixels or more. And also because this data is digitally recorded, it can be analyzed and shared immediately, which is very convenient. Now, you don't have to go develop a picture and things like that. And you can then email it to your associates. And once you have information digitally, you can sharpen images with image processing. So you can get more detail by processing the image. Especially, if you know some stuff about what you're supposed to be looking at, you can get better resolution. Another thing that you can use that's very useful when you observe things is spectroscopy. We discussed the advantages of using spectroscopy on various objects. So most telescopes have some form of spectrograph or spectroscope. And they use a device that splits the light into its component colors and wavelengths. This could be a prism, this could be a diffraction grating, this just depends on what you're doing. And then that spectrum is usually expressed onto a CCD. So there's the ones they use in the spectroscopes are these long strips. So you put out like a rainbow and the pixels are all lined up across. And that can be recorded on the CCD and analyzed, and this can tell us about the motion, composition, temperature, etc. of astronomical objects. So astronomical detectors, we can use them to make images, record images, make a permanent record of what we see through a telescope. Modern telescopes primarily use charge-coupled devices to digitally record images and spectra, at least for visible light. For different wavelengths, you have to use different detectors. So like the yttrium, I don't know. For infrared, you use different detectors, made of different stuff, because they have to react to infrared light instead of visible light. And they often have to be actively cooled. And then digital images and spectra can be easily and quickly shared with astronomers in different locations. Now, so those were optical telescopes. Let's talk about radio telescopes. Radio telescopes detect radio waves. Like visible light, radio waves can penetrate the atmosphere. So the two primary types of telescopes we have on Earth are radio telescopes and optical telescopes. Optical telescopes see through the optical window, which is visible light and a little bit of ultraviolet and a little bit of infrared. Radio telescopes see the radio waves that make it through the atmosphere. And they can be observed from the ground. This gives us an entirely new view on the universe and has a number of additional advantages. Radio telescopes can be used during the day because the sun doesn't actually put out a huge amount of radio waves, unlike visible light. So they don't get blasted out. Also, radio waves don't care about weather. They will just go through clouds and most of the other things in the atmosphere that get in the way. The stuff in the atmosphere is just literally too small to affect the radio waves. They're not sound waves. You can't hear them unless you have a radio, which detects the radio waves and converts them into vibrations. And yeah. So radio waves are very similar to optical reflecting telescopes. they have a large mirror, the dish. They tend to be prime focus, because the detector doesn't need to be huge, and radio mirrors are sort of big and awkward, so it's easier just to put a detector at the right place out on an arm, as you can see here. So this is the mirror, this is the focus. And because radio waves are larger, their mirrors are less sensitive to imperfections. So they don't have to be perfectly smooth glass surfaces. They can be metal mesh. Because the wavelengths are longer, because they're less sensitive to imperfections, you can make metal mesh and make it very large. So radio telescopes get real big. This is, I think this is the Green Bank telescope in West Virginia, which is the largest movable radio telescope in the world. And for scale, it's hard to give you an idea of how ridiculously big this thing is. But this is a building like there's a room over here. So let's look at some very early radio astronomy. Earliest radio astronomy basically was let's stretch out some antennas on the ground and see what we detect. So Carl Yansky in the 1930s was studying radio communication, because in the 30s, radio was relatively new as a technology. And he found radio waves from some unknown source. And he realized they appeared 4 minutes earlier each day, which corresponds to the difference between the solar and sidereal day. That's the sidereal period of Earth. So, oh, they're coming from space. And what he had detected was actually the galactic center. Galactic center puts out a lot of radio waves. The stuff falling into the black hole in the galactic center puts out a lot of radio waves, but other stuff there doesn't. Now, radio waves let you see different things than you see with other wavelengths of light. So looking at things with various wavelengths of light is very useful. So this is the Crab Nebula. This is in radio waves. This is in infrared. This is visible light, ultraviolet, X-rays, and gamma rays. So what you can study with radio waves, one of the things that you can study with radio waves that you can't study with anything else are cool objects, big molecular clouds. Because it turns out there's a transition in molecular, in hydrogen. Well, you can also, basically, radio waves let you study big clouds of gas out throughout the universe. Because it turns out there's a transition in hydrogen that can occur that's fairly low energy, but because of this, it happens very often. And it puts out radio waves that are 21 centimeters long. It has to do with the electron flipping between aligned and unaligned with the magnetic field of the proton. That puts out radio waves. So it's good for cool objects and also certain extremely energetic objects where electrons are being accelerated. So stuff falling into a black hole pumps out radio waves. Other things like that. The longer wavelengths, though, mean much poorer angular resolution. So you need much bigger dishes. Some advantages of radio astronomy. It works 24 hours a day. Doesn't matter whether it's day or night, because the sun doesn't pump out enough radio waves to be an issue. Clouds, rain, and snow don't interfere, because they're too small to interfere with the radio waves. And then observations at an entirely different frequency get totally different information. So here's an active galaxy, and here are the streams of material being spit out of the center of that galaxy that you can only really observe in radio waves. Now, with this event, so we can observe 24/7, we get a different view of the universe. Radio waves also can much like they can penetrate weather, they can penetrate dust. So we can see inside dusty clouds, other areas that are difficult and obscure. So we use radio waves to see like into the clouds of gas and dust where stars are being born. We also use radio waves to see the surface of Venus because there's all those clouds in them. We can see cool hydrogen gas, which makes up much of the universe. So it lets us figure things out about what's going on in between galaxies in the large areas that are not pumping out lots of light. The disadvantages, the resolution is cruddy because the waves are so long. The resolution depends on the ratio between the size of your mirror and the length of your wave. Radio waves are really long waves, which is problematic. So radio telescopes need to be very large. And another issue can be on Earth, we are pumping out tons of radio waves. So, as I walk around every day, I am carrying multiple objects that emit radio waves on me right now. Every time I go to another slide, I'm emitting radio waves from this. My phone obviously emits radio waves. Bluetooth uses radio waves, lots of stuff. So that's an issue. Interference is a real issue. So that Green Bank telescope I showed you, it's actually in a radio, and lots of electronic devices generate radio waves. So there's a really funny story about, there was a strange observation made at a radio telescope a while back. They thought it, they weren't sure what it was, they were trying to identify it. It looked kind of like one of these weird things. They eventually traced back the source of this strange observation they made to a microwave in a break room. This is the problem. There's a really interesting paper on this about how they actually figured out that it was the microwave. But so one of the ways, so the biggest problem with radio telescopes from a practical sense is resolution. So the solution to that is interferometry. I mentioned interferometry earlier, that it's a way that you can combine information from multiple telescopes to effectively have a larger resolution. It can be done with optical telescopes, but it's hard because you have to do it all with optics. It turns out with radio telescopes, it's a lot easier because the waves oscillate more slowly. So we can actually record the oscillations and do it all digitally with math. Basically, the signal count, we can combine the signals more easily. The same object can be observed with multiple telescopes, and the signal can be combined, and we can do it either digitally or just electronically instead of optically. This increases the effective size of the telescope for resolution purposes to the distance between the telescopes. So this can match or exceed the resolution of optical telescopes, which is why a lot of these radio telescopes that are built are these large arrays, lots of dishes. So effectively you have a telescope the size of the large array that you built. So this is, I believe this is the very large array, which is sort of a huge Y-shaped array of radio dishes that are all pointable. Is that the very large array? Yeah, and they're working on an even bigger one right now. It's like a kilometer square or something. I don't remember exactly what it's called. So yeah, this is a better picture. Let's see this giant sort of Y-shaped structure. By combining information from several widely separated radio telescopes, it'll act as if it came from a single dish, and the resolution will be that of a dish whose diameter was equal to the largest separation between the dishes. It acts like one giant telescope. And interferometry requires preserving the phase relationship between waves over the distance between the individual telescopes. You're comparing the phases of the waves at each individual telescope. So that's much easier because the periods for radio waves are just much longer than the periods for optical. You can do this by literally combining light, which is what they do for optical telescopes. But you can do it electronically for radio telescopes, and it's much easier. And these telescopes can get radio audiences whose resolution is close to optical, as you can see here. And these are, yeah, so this is the radio image, this is the optical image. You can see the resolution is about the same. And in fact, the most impressive thing, piece of interferometry was the Event Horizon Telescope, which used an international network of radio telescopes around the world, where they recorded all their data onto hard drives, brought it all to one location, and did an enormous quantity of calculations at like a supercomputer to combine it to create an image of a black hole. So this is the black hole at the center of M83, which is the first one they imaged. They also imaged the black hole at the center of our own galaxy, but they started with one in M83 because there's less possible interfering stuff in between. They're about the same size as the sky because this is a much bigger black hole than the one in the center of our galaxy. But there's less gas and dust in M83 than there is in our galaxy. Yes.
Is it like endless?
Well, black holes. So there's a black hole at the center of this. This is the material falling into it. A black hole is just super, super compressed. It's basically the point where gravity wins over everything else. So a black hole is sort of, it's not endless, but there's a point of no return. It's called a black hole because nothing can escape, not even light. So it is perfectly black. Because gravity is so strong, light can't even escape. That's the definition of a black hole. We don't know what's going on inside a black hole, but the theory is that you can solve the equations of general relativity with what's called the singularity. It's a mathematical term, where effectively all of the mass can be concentrated into a single point of, effectively infinite gravity. Doesn't necessarily mean that's actually what happens. We don't know.
It's where
It's where gravity wins.
density increases and gravity increases, but increasing gravity causes an increase in density.
Yeah.
Perpetuating.
So there's a point where there's just nothing that can push back against gravity. As it increases, as the thing compacts. And eventually it just collapses, severs itself from the rest of the universe effectively, because anything that goes in can't come out. So nothing can come out. And then you get a black hole. We know they exist. We can make sure we do not know what is going on inside a black hole. Like that's where the conditions are so extreme we don't know what happens. There are some theories, but we can't look because nothing can come out. Because it's effectively severed from the rest of the universe. And there's some other weird stuff that goes on with black holes. We will discuss black holes later in the semester, but it's going to be a while. And interferometry, as I mentioned, can also be done with visible light, but it's much harder because of the shorter range. Because you can't do it electronically, you have to do it with very carefully aligned optics. So, the 300-foot Green Bank telescope collapsed in 1988. It was rebuilt in 2000. This is the Green Bank telescope. This is the 100-meter Robertson Baird radio telescope. And the reason it's in Green Bank, West Virginia, is because that's the middle of a military testing area that is radio silent. No one is allowed to have anything that emits radio waves for a large area around it, because that's where the military tests its radio technology and such. And just for scale, this is a room. You can go up there, go in this room, when the telescope is more vertical. But yeah, like this thing is huge. Like this is a reasonably sized tall fence down here. And this is the largest fully steerable radio telescope in the world. So there are bigger radio telescopes, but their dishes are set in the ground. So you can't point them in any direction. You can change the direction a little bit by basically changing where you put the detector. But they're you can make it bigger, but they become more limited in other ways. This is the biggest fully steerable telescope. It can point any which way. They can actually tilt this down so the edge of this basically comes to the ground. And stuff. There's a good Tom Scott video where he visits this telescope. And it just gives you a much better idea of the scale when you see an actual person inside that crazy structure. This was the biggest radio telescope made in the US. It was the biggest in the world for a while, up until 2016. And it was the biggest telescope that could do radar. This is the 300-meter Arecibo telescope. If you watched GoldenEye, it showed up in GoldenEye, I believe. It's in Puerto Rico. It was completed in 1963. And in 2016, up till 2016, it was the largest single-dish radio telescope. In 2016, the FAST in China was built, which is 500 meters across, but FAST in China couldn't do radar measurements. And unfortunately, it recently was destroyed. When basically it was old, it was built in the 60s, and it turns out some of the parts of it holding the cables were not built to the best specifications. A cable came free. Eventually, one of these cables on the side, it had been, so a cable broke. They closed it because of that. It was still up, and then they were it actually failed while they were inspecting the cables with a drone. So a cable came free, and then the whole thing collapsed. And because somebody had a camera in their office pointed at the telescope, and because they were inspecting with the drone, we have video. And it looks like, yeah, it had been years of poor maintenance because it had sort of been tossed from. And then this is the drone footage. So this was in 2020. So here you can see the cables were clearly damaged. One of them had already broken. They were trying to work out how they might possibly repair them. And then the blew apart. It turns out there were issues with the way they were anchored. Yeah. And then the whole thing collapsed. And it is not going to be repaired, is what it looks like at the moment. Unfortunately. So here are some future radio telescopes. The square kilometer array is projected to be completed in 2027. There's also the next generation very large array, which is in planning and projected to be completed sometime in 2035. Astronomy projects, telescope projects are planned decades in advance, especially space telescopes. So radio waves also penetrate the atmosphere. They can be studied from the surface of the Earth, and radio observations give us a completely different view on the universe. And interferometry is used to greatly increase the resolution of radio telescopes. And I saw there were some chat messages. So let's talk about the last place we put telescopes, in space. So only a small portion of the electromagnetic spectrum actually makes it to the ground on Earth. Most of it is blocked by the atmosphere. So if we want to detect it, we need to go above the atmosphere. So we put telescopes in space. This gives us entirely different views of the universe. As you can see here, different wavelengths let us see different things, different aspects of the Crab Nebula. For example. The Crab Nebula is interesting because this is a supernova remnant. This is what's left after a large star exploded in about 1,000 years ago, 10, 20 something. The actual supernova was recorded for this particular nebula. So this is young. So for example, infrared radiation penetrates through dust because of its longer wavelength. So infrared radiation can image where visible radiation is blocked by interstellar matter or atmospheric particles. So on Earth, hazy day, much clearer when viewed in the infrared. Because it just goes around the droplets. Here we have a nebula, hazy nebula. We can see all the stars inside in the infrared. Now, infrared observatories, you need to get above the water vapor in the troposphere. Water vapor absorbs infrared light. So you need to get above the lowest layer of the atmosphere. One of the ways is we use balloons and aircraft. They send telescopes up on weather balloons. And there was Sophia, which is a 747 with an infrared telescope in the back. Sophia, I think, has been grounded at this point. They're not running it anymore. Or we use spacecraft. IRAS or Spitzer were some of them. So you can send up a balloon, or you can put something into space. And so infrared telescopes in space. The most famous of these is the James Webb Space Telescope. It's primarily an infrared telescope. It does actually also go into the visible, but mostly infrared. And then Spitzer was one of the first ones. So, but IR detectors need to be cooled. Because otherwise the heat of the detector activates the if you're warm, you're emitting infrared light, which sets off your detector. Otherwise it would be emitting the type of radiation it's trying to detect. Not very helpful. So Spitzer used a method where it evaporated off material to cool. James Webb has a dilution refrigerator in it. No, it has a pulse tube in it, sorry. I think it might also have a dilution refrigerator. I need to check. But it has an active cooling system that cools it down to like within like 1 Kelvin or something. But it uses a refrigeration cycle. with helium instead of other refrigerants. The Hubble Space Telescope was launched in April 24, 1990. It has a 2.4 meter mirror. That size was basically the Hubble Space Telescope is the size of the space shuttle bay. That's what determined the scale of this telescope. It's above the Earth's atmosphere, so there's no atmospheric interference, and it can observe infrared and UV in addition to visible. There was initially an issue with the mirror. It was ground slightly wrong. But the Hubble Space Telescope was designed to be modifiable while the space shuttle existed. So they did a mission up there and put in some corrective optics. They fixed it. Basically, it was ground slightly wrong, so stuff was a little distorted and out of focus. They added a couple extra mirrors, after the mirror to fix that, basically. It has a number of instruments that could in theory be swapped out, but can't anymore because we don't have the space shuttle anymore. Because it was designed to be serviced by the space shuttle. It's still working though, even though a bunch of stuff on it is broken. And the resolution of the Hubble Space Telescope is quite impressive. We saw some things we never thought we would see, like what we saw with the Hubble Dark Field image, where they pointed the Hubble telescope at a dark spot of the sky and just saw what they could see. It was sort of a shot in the dark. But they saw this really fascinating image of the early universe and these early galaxies. Tons of them. There are also, if you want to observe shorter wavelengths, higher energy light. So UV, X-ray, and gamma ray observatories need to be done above the atmosphere because the atmosphere absorbs those wavelengths. So the International Ultraviolet Explorer was out from 1978 to 1996. The Chandra X-ray Observatory was launched in 1999, and the Fermi Gamma Ray Telescope was launched in 2008. To focus X-rays and gamma rays is harder. You need to use weird glancing mirror stacks to focus X-rays. For gamma rays, you can't actually really focus them. They're just too energetic. They just slam into stuff and interact with them. So this is the Ultraviolet Explorer, this is the Chandra X-ray, and this is the Fermi Gamma Ray Telescope. So ultraviolet images. So this is the Cygnus Loop supernova remnant. This is M81. These are some ultraviolet images. X-rays and gamma rays don't reflect off mirrors in a normal way. They're just so energetic they would violently interact with the material that makes up the mirror. So you need new techniques. So X-rays you can bounce at a very shallow angle, so they have nested cylindrical mirrors like this to focus X-rays. And gamma rays, you basically just put detectors up there with tubes to get a direction. So this is an X-ray image with the supernova remnant Cassiopeia A. And gamma rays are the most high energy radiation we can detect. And this supernova remnant will be nearly invisible without the Fermi satellite and its gamma ray detector. And a lot can be learned by observing the same astronomical object in different wavelengths. So here are different images of the Milky Way, going from radio to infrared to visible to X-rays to gamma rays. And the James Webb Space Telescope was launched in 2021 on December 25th, Christmas. It has a 6.5 meter mirror made up of a number of segments, as you can see here. It detects red, orange, and infrared light, and its orbit is out past the moon. So it's in an orbit around the sun, past the orbit of the moon. And it's where gravity sort of balances between the combined gravity of the Earth and the sun let it orbit at the same rate as the Earth around the sun. It's out of the range is what it's called. And it's way out there so that there's nothing in the way of what it's observing, basically. And this is a sun shield to protect it from the sun, so the telescope can observe in shadow. And then all the equipment is down here. And this was all folded up to fit inside a rocket. And it launched from Earth and settled at L2. And it's orbiting around the tactical L2 point because the exact L2 point is in the shadow of Earth and it needs to have solar panels working to power things. And this is a repeat of that deep field observation that Hubble took, where they got a better picture in 12 hours, as opposed to what took weeks for Hubble. So it's a much more powerful telescope. This is what Hubble did. This took weeks, this took 12 hours. So only visible light and radio waves can penetrate the atmosphere to be observed from the Earth's surface. Space telescopes give us a new view on the universe because we can observe without having to look through the Earth's atmosphere, and future telescopes are planned to continue observing from space. So here's just a summary. Refracting telescopes make images with a lens. You can read this on your own time. It's the end of class. Have a nice day. I mean, this is I ran over by a minute, sorry. But that's just a summary. Regarding why they can't send things to fix Hubble, it's because we don't have anything that can actually do it at the moment. Because it was designed to interface with the space shuttle. I'm going to end the meeting. Yeah, but it was repaired while we had the space shuttle.
Like the weekend, like general, like the date is selected, number 6 and so all that July. I would also
And
I'm still gonna work it's like 3 days to do who knows when this time.
because of the way it's designed, it needs like the arm on the space shuttle to hold it in place. So you can do a spacewalk up to it to work on it. That's the issue with the Hubble. I'm going